Hello guys, so welcome back to our lectures. So we're gonna continue talking about numbers, and today is our topic is about hexadecimal number. So we talked about decimal numbers, we talked about binary numbers, okay? But how about if we or base 2 and the base 10? Base 2 is binary, base 10 is decimal. How about other bases like a base 8, base 5, base 6, base 16 maybe? Okay, actually we can create whatever base we need, base n in general. Okay, and hexadecimal numbers, or hex, usually it's called hex, are base 16. So we're gonna start by the journey that led us to using such system, and why it's important and why it's really human readable, we can say. Okay, so let's start. First, how computer stores data or information. So computers knows just electric charge. He recognized, or she, I don't know. So it recognizes the absence of electricity, the presence of electricity, the absence of a charge, which is 0 or can be represented as 0, and the presence of a charge, which is 1, we can say. Okay, so two distinctive situations. So it knows basically binary numbers, because 0 and 1 is just base 2, binary. Computer memory stores charges, or doesn't it store? So it's again zeros and ones, either storing some charge or there is no charge, so 0. Computer storage, HDD, it's a drive, hard drive. Okay, again zeros and ones. The communication between, for example, the CPU and the memory or the hard disk, again it's zeros and ones. So computer just know zeros and ones. Good, binary. Sometimes we have a huge set of data, okay? So it's hard for us to to recognize easily the size of this data if we measure it in bits, like for example 1,700,000 whatever bits. It's really not memorizable easily. So we use for this some prefixes like kilo, mega, giga, tera, which is 1 trillion, okay, beta and exa, and so on. There are many of these. Okay, so we use these prefixes to reduce the numbers basically, so that we can memorize easily the specifications, for example, of a memory or a CPU or whatever. But in binary systems or binary system base 2, it's not, kilo here is not like our kilo. Our kilo is usually in 1000, but in our binary system, since we are talking about base 2, kilo here is 2 to the power of 10, which is 1024. See, so 1024 is our kilo here. This is our kilo, which is basically 2 to the power of 10. So for example, kilobyte, KP, K capital, B capital. This is 1024 bytes, and the byte is 8 bits. 1 mega, mega is 2 to the power of 10, or kilo multiplied by a kilo, or 2 to the power of 10 multiplied by 2 to the power of 10, which is 2 to the power of 20. which is 1,000,000, 48,576. It's really bad to, it's not memorizable at all. But if we say 1 megabyte, that's easily to, to recognize or to memorize. Or even, 1,024 kilobyte. But of course, 1 mega is much easier. Giga is basically 2 to the power of 10, 2 to the power of 10, 2 to the power of 10, which is 2 to the power of 30. And again, memorizing this number, even, trying to say it, it's hard, but just saying 1 giga, you know it, or you can, determine or calculate it in a very easy way, which is 2 to the power of 30. That's it. Okay. 1 tera, just add 2 to the power of 10 to the equation. So 2 to the power of 10, 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 2 to the power of 40. 1 terabyte. Of course, again, this number here is really, hard to memorize and even say. Okay. So basically what we want to say here is that usually with computers, we have very large numbers, okay? And we need some prefixes or some way, to say or, to memorize, these numbers. So we added these prefixes. And that's the first clue, or the first reason we can say why we will need hexadecimal numbers. Just a small note here, byte versus bits. Byte, so byte is usually B capital, bit is usually B small. So M capital, B capital means megabyte, byte. M capital, B small, that's megabits. And byte is equal to 8 bits. Okay. Here are all, the terminologies that we're gonna use in this course. Bit, which means binary digit. So if you have a number like this, so each digit here, it's called bit. These are all called digits, basically binary digits. We take the B, we take the IT, and we call it bit. Nibble is 4 bits. So if you take here any portion like this one, this is 4-bit portion, it's called nibble. Byte is 8 bits. So if you have any 8 bits, any 8, like this has a whole is byte, 1 byte. And the byte basically is 2 nibbles or nibbles. And each nibble is just 1 bit. Word is actually, has, many definitions. And it's not a standard. So byte is 8 bits all the time. But the word length, is basically based on the system that you are working with, the processor itself. So sometimes the word is just 8 bits like byte. Then, we have other processors that have word length of 16 bits, 2 bytes, and there are 4 bytes, 32 bits. And now most of the processors are 64. So the word length is 64 bits. Okay. So it depends on the architecture, depends on the processor. So it will be given for you. But byte all the time 8 bits, nibble all the time is 4 bits, and the bit is just 1 bit. Okay. base n systems. So we said that with computers, we deal with very big, usually very big numbers. Okay. And for this, we used the, the prefixes kilo, mega, tera, giga. Okay. Another way to do that is using base n. Okay. And we have many bases. You can put in whatever you like. If n is 2, it's a binary. If n is 3, it's trinary, and so on. If n is 10, it's decimal. If n is 16, is hexadecimal. There is also octal, which is a system that was used before, but it's migrated now. So now we will see binary, decimal, hexa only. You will not see octal or anything else. Okay. So why we need or base n, and n here is 16. Okay, let's first define the base 16. So base 16 number or hexadecimal number or hex number, okay, we said that with base 2 we need two symbols, 0 and 1. With base 10, which is decimal, we need numbers from 0 to 9, 10 symbols. With base 16 now, we need 15. We need 16 symbols. Okay, so we use numbers from 0 to 9. Then A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. So these are 16 different symbols. 0 to 9, then A, B, C, D, E, F. After that, you will have some way of continuation. We're going to see it in a moment. So A again stands for the number 10, B stands for the number 11, until you reach F stands for the number 15. And these are, the first 16, digits, we can say, if you are counting in hexadecimal. To give you a clue why we need this, let's write F. F with hexadecimal is just one symbol. You write just one thing. Easy to write, right? With decimal, this is 15. So two symbols. How about binary? It's 1, 1, 1, 1. 15 in binary is just for 1. So 4 symbols. So here's just one symbol, 2 symbols, 4 symbols. So that's, a way to decrease or shrink or make a number compact. And at the same time, it's human readable. I mean, when you look at F, it's easy to memorize. Oh, this is 15. And that's why we use, hexadecimal numbers, because it make big numbers very compact. And by the way, decimal is also doing the same, but it's less compact than hexadecimal. Because look, here is 4 bits. With decimal, it's 2 bits, 2 digits, we can say, 2 symbols, 2 stuff you write, 1 and 5. But hex is, is very compact, just one symbol. Okay. Here are examples for hexadecimal numbers. A, which is 10, 9 is 9. Okay. 1001. You must here say this is hexa, because 1001 can be hexadecimal, can be binary, because 1 and 0 depend, it's the basis for the binary numbers. And 1 and 0 also belong to decimal numbers. So you must here say this is binary number. But of course, 9C5, that's hexadecimal without giving any notation or something, because C is, there is no C in binary and decimal. BFE is another number, although it's like a word, it's like English, but this is just a number, okay? Etc. Of course doesn't mean this is not a number. This is just, saying etc. We can write whatever numbers as long as you are within the 16 symbols that you have, 0 to 9s in A, B, C, D, E, F. Okay, so that's a number. It's a human readable, easy to recognize, easy to memorize, but this is maybe the difficulty with hexadecimal. It needs a conversion, but the conversion is really easy, and that is a very basic advantage of hexadecimal numbers. Very easy to convert to binary, as we will see now. This is again, a confirmation for the clue that I said, that for any number in hexadecimal, it's usually very compact than decimal and than binary. And here are examples. With 15, you have just one symbol in hexa and 2 digits, or 2 symbols in decimal, same as for the other guys. That's why it's a shorthand for writing, binary numbers. And as a general rule, the length of hexadecimal number is 1/4 its equivalent binary number, 1/4. That's a general rule. Just look here, 0 to 15, all these are 4 bits. And here you have just 1 digit. And as we will see in a moment, it's very easy to convert from hexa to binary, and from binary to hexa as well. For example, let's say we have a number that is 1 1 1 0 0 0 1 1. Okay, that's a number, in binary, of course, and we want its hexadecimal equivalent. What you do when you convert, you do grouping. So you have chunks of nibbles, 4 bits, okay, and you just see what is the equivalent in binary in of these 4 bits. For example, we have here 8 bits, so you have 1 nibble here and another nibble here. Okay, so what is this one here? 0 0 1 1 0 0 1 1. It is it is 3 in hexadecimal. And it's 3 in decimal as well, What is 1 1 1 0? That's E. Very easy, very simple. Okay, how about if you have a binary number that is not multiple of 4s, like for example 0 1 0 1 1 0 1 1 and 1 0. This is again binary, and we want its hexadecimal equivalent. What you do here, you add zeros to the left. So you have here 4 bits, and 2 bits. You just add 2 zeros. So this will be now, because these 2 zeros will not affect the real meaning or the real value of this number. When you convert 0 1 0 1 1 0 1 1 1 0 to decimal, for example, it will be the same as 0 1 0 1 1 0 1 1 1 0 0 0. So 1 0 1 0 Where is it? It is that one here. It's A, 10. 1101, it's D. 0001, it's just 1. Now, how to convert from hexa to binary? That's also extremely easy. So let's take, for example, 1CC. This is a number. We want to convert it to binary. Okay, so you have here 3 numbers. Each number has some binary equivalent. So C is 1100. C again 1100, and 1 is 0001. Always write it in a 4 bits. Very simple. It's binary, and this is of course hex. And all the time, you can check that this rule is okay. The length of a hexadecimal number is 1/4 its equivalent binary number. Here is, for example, we have 12 bits. Here we have 3 bits. 12 over 3 is 4. Now, how to convert from hexadecimal to decimal and vice versa. That's exactly the same as what we did with, converting from binary to hexadecimal. We just multiply each digit, each bit, okay, with, power of 16, like 16 to the power of 0, 16 to the power of 1, 16 to the power of 2, and so on. Let's have examples. Like this number here, A12F. What you're gonna do is the following. So you're gonna multiply F. F is 15. So you convert F to its equivalent, which is 15. So 15 multiplied by 1, which is, or 16 to the power of 0. 1 here is 16 to the power of 0. Plus 2 multiplied by 16 to the power of 1. Plus 1 multiplied by 16 to the power of 2. 16 to the power of 2 is 256. Plus A, which is 10, multiplied by 16 to the power of 3, which is 4096. And this will give you 41263. That's really big number. Even to say 41,263. But this one is A12F. A12F is really easy to say. This is another example. 1028. Okay, so 8 multiplied by 16 to the power of 0, which is 1. 2 multiplied by 16 to the power of 1. 1 multiplied by 16 to the power of 2, which is 256. And finally, 1 multiplied by 16 to the power of 3, which is 4096. This is another example, really easy one. Another one. If here we can do it. So 8 multiplied by 16 to the power of 0, which is 1, plus A, which is 10 multiplied by 16 to the power of 1, plus F, which is 15 multiplied by 16 to the power of 2. So 15 to 56 plus 160 plus A plus 8. This will give you this number here, 4008. These are other examples, just explore it. Another example also for a bigger number. But here, look, just to compare this number here with this number. Look how far, or these two from each other. To convert from decimal to hexadecimal or hex, we again do the division. Just write what we did, like what we did with decimal to binary. Okay, we do the division. So we divide by 16 each time, and the remainder will be, part of the final answer. Like for example, convert 1128 to hexadecimal. So we divide by 16. This will give us 70 and remainder of 8. Then 70 divided by 16 will give you 4, remainder 6. Then 4 divided by 6, and this is the last step. Once you reach 4, that's it. Will give you 0, remainder 4. This is the most significant bit, or we can say left most digit, and this is the least significant bit or digit, which is the rightmost. So 1128 base 10 is equivalent to 864 base 16. And here are other examples with exactly the same concept. Okay, guys, thank you very much for watching this video, and see you in the next video. Bye-bye.